First of all, I'd like to thank the organizers for giving me an opportunity for being here and give a talk today. And I'd like to speak about dark gamma-ray bursts and their host galaxies. First of all, how do we discover GRBs? I think that everyone here knows that we have two main observatories, space observatories. It's Swift and Fermi. They give us alert if any GRB occurs somewhere in space, and this information about the localization of the event and its brightness and maybe optical counterpart is distributed among ground-based observatories via GCN. And here you can see some details about timescales and accuracy of position. Swift provides more accurate positions, but Fermi may observe GRB in wider energy range. The first afterglow optical counterpart of long GRB, and surely I will speak about long GRBs here, was discovered in 1997 for GRB 970228. And this raised a question: are all long GRBs accompanied by optical afterglows? Further observations in next years showed that the discovery of an optical counterpart occurs only in 20 or 30% of cases, but in that time it was difficult to observe, to search and discover and observe optical afterglows immediately after the GRB trigger, and the average time of reaction of ground-based telescopes was about a few hours. This might be some bias why we didn't see any afterglows, optical afterglows for a very huge percent of bursts. But with the beginning of operating of Swift and many ground-based telescopes, robot telescopes with fast reaction time, this picture became slightly different. But still, there are some events, some bursts. Different people provide different numbers among 20% and 35%. The bursts for which we do not detect any optical afterglow or detect only faint optical afterglow despite our deep observations. And this we may call the problem of dark bursts. What does it mean, the dark burst? In synchrotron radiation produced by the GRB ejector, the photon index beta is connected to the index of electron energy distribution, P, either as P minus 1 divided by 2 or P divided by 2, depending on where the cooling break is. And in the simple blast wave model, P is expected to be larger than 2. And this provides that the spectral index calculated between optical and X-ray regime should be more than 0.5. And this allows to make some criterion to divide ordinary bursts and optically dark bursts. In 2004, Jacobson with co-authors suggested such a criterion. He suggested to take the optical flux, observed optical flux, and X-ray flux, and extrapolate or interpolate them to 11 hours after the burst beginning. Why 11? Because at that time it was something like an average time for ground-based big telescope reaction for the observations. To plot these fluxes together and to calculate the spectral index between the optical and X-ray regimes. And if the GRB, selected GRB, has this beta OX less than 0.5, this is classified like a dark burst. In 2009, Van der Horst with co-authors suggested a slightly different criterion, which did not require any assumption on temporal evolution of the burst afterglows, but only one assumption about that the X-ray and the optical components are produced by the same mechanism. And in this case, the optical spectral index beta, which is calculated only in by optical flux, should be equal to beta calculated by X-ray flux, or to beta x minus 0.5, depending on where the cooling break is. And if we, in this case, beta OX, which is calculated between optical and X-ray, should be between these two values. And if we have beta OX less than this value, the burst is classified as dark. In simpler words, and if we have a picture, we may say that dark bursts have bright X-ray radiation in one time with faint optical radiation. Here you can see some plots from Greiner's page. These two examples are ordinary optically bright bursts, and you can see X-ray and optical here, and standard spectrum, synchrotron spectrum without a break between these two regimes and with a break, for an example. And here this is an example of a dark burst where you can see that observed optical flux does not fit the standard synchrotron spectrum, and this burst may be classified as dark because it has very faint optical afterglow in comparison with X-ray afterglow. What could be the nature of the darkness of the bursts, GRBs? First of all, if we, as we know, the gamma ray bursts are cosmological events, and they lie on cosmological distances, and the first thought may be about the high distance, high redshift. Indeed, for redshift more or equal 4, optical radiation is effectively absorbed in Lyman alpha forest, and if we observe the optical counterpart in ordinary R filter, we do not see anything. But if we observe in infrared, we may discover the optical afterglow. The problem is that infrared observations are not so widely spread in our world today, and they are not so easy to provide like ordinary optical observations. But further investigations showed that this reason for the burst to be dark, high redshift, occurs only in 10, maybe 20% of the total number of dark bursts. And the good example for this case, maybe GRB 08, 09, 13 with a very high redshift, Z about 6.7. The second and very solid reason for the burst to be dark is absorption. And there are two different kinds of absorption. First, it's the absorption in the medium of the host galaxies, so-called bulk absorption. It's an average value of absorption calculated to the young stars situated somewhere in the middle of the galaxy. And we just calculate the average absorption in the thin, optically thin parts of the galaxy. And this value I will further call AV host.
I mean, you also expect absorption of the X-rays.
Yes, but not so high as for the optical, because you see, if we have average absorption in the galaxy about 0.8 magnitudes, and we place the galaxy at Z2, we do not see significant absorption of X-rays, but we see 3 magnitude absorption of optical. So it affects more optical than X-rays.
Yeah, no, that's totally right. X-ray absorption is decreasing very rapidly as 1/4 photon energy cubed in the X-ray band. At 10 keV, for instance, there's very little absorption. Now, if you're looking at redshift of a few, as she is talking about, then 10 keV in our frame is 30 keV in the host galaxy redshift, and there's really practically no absorption at that energy.
Yeah, thank you. And
I just want to add, there's numerous cases all over the place where gas does not reflect dust, and it'll be dust that's killing you here. There are many cases in extragalactic astronomy where gas does not reflect the amount of dust, and basically the dust can completely extinguish this.
thank you. And the second kind of absorption may be some specific line of sight absorption, some clumps, clouds, some shields, maybe envelope around the burst source. And here I have a picture. If we have the source here and we have our line of sight and something between us and the GRB source, we may have a very big extinction. There are examples for extinction about 10 magnitudes or even higher. And this value I will call further AV loss from line of sight absorption. And of course, our assumption that optical and X-ray mechanisms are the same mechanism may be wrong. And there are a few cases of that may be an example for this explanation, but I won't stop on them in my talk, and I give you some links if you want to learn about it more. So, what is the difference between dark bursts and bright bursts? Are they the same events, or maybe they are events of two different classes, not only by observation but physically? Let's compare their properties. Firstly, I'd like to compare to show you a comparison of their prompt properties. It's E ISO, so-called isotropic equivalent energy, E peak, it's peak energy in the spectrum, and L ISO, isotropic luminosity. And Melandri with co-authors did this comparison. They took about 50 bursts which were bright enough in gamma rays and had favorable conditions for ground-based observations and had measured redshifts. to make the sample homogeneous. They compared these properties and find that dark GRBs and optically bright GRBs do not differ in these terms. So they are the events from the same sample of events. But they slightly differ if we talk about observed X-rays and optics. Here you may see, I forgot that blue are dark bursts and red are non-dark bursts, and the fraction of dark bursts in their sample is about 20%. And here you may see the distribution of X-ray luminosity extrapolated for 11 hours after the burst trigger, and observed X-ray flux and observed optical flux. And in the same time, dark bursts tend to be in the lower end, lower tail of optical distribution, and in the higher tail of X-ray distribution. The explanation of this fact may be the difference between their environment. If dark burst sources are situated in dustier environments, this dustier and more metal-rich environments, this may occur. What we see in these diagrams may occur. Speaking about surrounding medium, here I give you two pictures. This is the plot of AV loss. It's absorption on the line of sight against redshift, taken from Covino and Cawthor's paper. And here the colors are inversed. So red are dark bursts and the blue are non-dark bursts. And we may see that dark bursts tend to be more obscured on the line of sight, and nearly 40% of dark bursts have AV loss more than 2 magnitudes, and for optically bright bursts, this fraction is only about 5%. And also, here you may see the distribution of hydrogen column density. Red is for dark bursts and black is for non-dark bursts. And the average hydrogen column density of dark bursts is higher than that of optically bright bursts, approximately by an order. If we speak about surrounding medium of the bursts, we logically come further to the properties of their host galaxies. In general, GRB hosts are blue star-forming galaxies with color index B minus R about 0.3, 0.7, with the median brightness minus 20 magnitudes. But one can also see among them dusty and red galaxies, like the host galaxy of the GRB 070521. But if we speak about dark bursts and non-detection of optical counterpart, in these cases, the observation, the search and the observation of the host galaxy may be the only way to determine the distance to the source of the burst and to determine its intrinsic parameters. Currently, host galaxies of long GRBs have been found and studied at the redshifts as high as 4.7 for GRB 100219A. If we investigate the host galaxies of dark GRBs, it may help us to determine the nature of the darkness of this GRB, this specific GRB, if it is high redshift or if it is absorption of some kind, maybe a different type of radiation mechanism. But in case of dark bursts, we may expect some problems because their host galaxies are usually very faint galaxies, tiny I mean in angular size. And if we have no detection of the optical afterglow, so we have no exact position of the GRB source, we have only some error circle from Swift XRT, and this may be several arc seconds. And in this error circle, we may find not one galaxy, but few galaxies, and which one is our galaxy, we don't know. And this is quite a problem. If we compare the properties of host galaxies of dark GRBs and bright GRBs, we may see that firstly, dark GRBs tend to occur in redder galaxies. Here you may see the color index R-K, and here is redshift. Red points are dark bursts, and blue points are non-dark bursts, and gray circles are filled galaxies. This is a plot from the work of Perley with co-authors. If we compare the average host extinction, we also may see that dark GRBs, also red points here, prefer more obscured, more dusty galaxies. And non-dark GRBs prefer more transparent galaxies. And talking about AV and the host galaxy average AV and the AV on the line of sight, what we may see from the afterglow absorption, observations. Here is the plot comparing the line of sight extinction and the average host extinction. And this gray area is the equality of the two values, when we may assume that the medium in the galaxy is distributed rather homogeneously when we calculate the average extinction to the average star in the middle of the galaxy, and it is more or less equal to the specific AV to one specific source. But you also may see there are some outliers, and here lie the bursts which are unobscured, so-called optically bright, and they lie in dusty galaxies. They have rather big value of AV host. And in this corner, it's controversial, there are obscured GRBs, dark GRBs, in rather unobscured galaxies. And the fact that we may see that dark bursts, red points here, prefer more dustier galaxies on average, but there are some cases when dark burst is situated in not so dusty galaxy, and this may give us a conclusion that dark bursts prefer the galaxies with less homogeneous distribution of the medium, where the individual line of sight absorption to an individual source may deviate from the average magnitude for very big value. And also, I would like to compare the star formation rates of the galaxies, of host galaxies, of dark and non-dark GRBs. Here you may see Z, and this is SFR. Red points are dark bursts, blue points are non-dark bursts. And it's clearly seen that dark bursts prefer the galaxies with higher star formation rate. But all those diagrams that you have seen here, on all those diagrams, every point is a single galaxy, single GRB, single event. And to place another point on those plots, we need to discover another GRB, to find its host, to investigate its host, and to determine all those parameters, to place only one point. And I would like to tell you about an example of such a long and rather hard work. It's our original results. Dark gamma ray burst 05-10-08. It happened in 2005, and this burst was rather dark. Only X-ray afterglow was discovered. I'm sorry. Was discovered, and starting 30 minutes after the burst trigger. The observations, optical observations, were as deep as 22.5 magnitude, and in these observations we didn't detect any optical counterpart. And we calculated the beta OX as 0.02, so it's very dark burst. But half a year later, in Crimean Observatory on SHINE telescope, we discovered the host galaxy. It is this tiny spot here, labeled like ID3. This galaxy has R magnitude about 24. So it's rather hard to make spectral observations of the galaxy, to measure redshift directly. And when we managed to obtain a spectrum on Keck telescope, we saw that it is without features, and we also could not determine the redshift via spectral observations. So we performed optical observations in many optical filters, U, B, G, V, R, 2I filters, Z, K, and we determined the redshift photometrically. Photometrical shift technique is when we have broadband spectrum from the optical observations, and we have some spectral energy distribution libraries for galaxies which are modeled, and we fit our observations and the library spectrum, and we find something like this. We found that the host of the burst is a Lyman break starburst galaxy at redshift about 3, more exact 2.8. It's a rather bright galaxy with absolute magnitude in the R filter about -21, and moderately obscured galaxy with AV host about half a magnitude. And it is extremely star-forming galaxy with very high star formation rate. The fact that we determined the redshift allowed us to determine some GRB properties like equivalent isotropic energy and the energy ejected in gamma rays. The range depends on what profile of the ISM we have. It's a constant ISM or wind profile. Question?
You mentioned the EIs, they are only equivalent, right?
Sorry?
Did you estimate this opening angle?
Opening angle, yeah, we have the X-ray light curve with the break.
Oh.
So if we assume that the break is the same in optics and in X-ray, we may estimate the jet opening angle. And we calculate, we have some constraints on the line of sight extinction. It's more than 6 magnitudes, and this allowed us to make a conclusion that this burst is dark because of significant absorption on the line of sight. Then this allowed us to place this GRB like another point on all those diagrams, and you may see that all the parameters are on average the same for the other dark GRBs. So it's dusty GRB in moderate dusty galaxies with very high star formation rate. So I go to my summary. Still, we have about 20% of events of gamma ray bursts for which we do not detect any optical afterglow or detect very faint optical afterglow. But we may see that the sources of dark bursts do not differ from the sources of bright bursts. But on average, dark bursts have higher X-ray luminosities and lower optical observed flux. Dark bursts, on average, tend to be located in a medium with higher values of hydrogen column densities and with higher extinction to the line of sight. They tend to prefer more dusty, more red, more star-forming galaxies. And in most cases, dark GRBs are dark because of the significant absorption. Is it bulk absorption in the galaxy or absorption on the line of sight? Thank you.